Hi, I'm Paul Gorman, and today we're going to be talking about electromagnetic interference in PCB design, the war between current and noise. So, what are we even talking about? Well, PCBs, or printed circuit boards, are the electrical and physical backbone of nearly every electronic device that we rely on. Everything from pacemakers and insulin pumps to automotive ECUs, smartphones, drones, arcade games, Nintendo Switch controllers. At their core, PCBs are just pieces of fiberglass and copper, but how they actually operate are as electromagnetic environments. Every trace is a conductor that carries time varying signals, every plane stores electric and magnetic energy, and every dielectric layer shapes how fields propagate. Electromagnetics is relevant because signals are not confined to the copper. They exist as electromagnetic waves traveling through the dielectric material between the traces and its return path. Whenever we change currents or voltages quickly, we generate electric and magnetic fields. And if those fields leak out, they couple into other circuits, or they have the chance of reflecting to other objects due to impedance mismatching. And the result of that is called EMI, or electromagnetic interference. So let's get into the math of it. Well, to design low EMI circuits, we directly apply the theories of this class, first being Biot-Savart's law. This tells us how current produces magnetic fields. If we route a high-speed trace without a solid ground return beneath it, the return current detours, increasing the loop area. And Biot-Savart's law predicts exactly how the magnetic field grows with loop size, which explains why even a simple routing decision can dramatically increase the radiated emissions. Next, we apply Faraday's law. A changing magnetic field induces voltage in a nearby conductor. This is the physics behind crosstalk and why switching regulator loops must be extremely tight. High current changes with respect to time create strong changing flux, and nearby loops become an unintentional receiver. We also treat long or fast traces as transmission lines. Maxwell's boundary condition, as we've discussed in class, helps us understand why a continuous ground plane is essential. The tangential electric field at the conductor must be zero, which forces return currents to flow directly under the signal. If we split the plane, we violate that boundary, and the return is forced into a larger loop, increasing field strength and EMI. Every aspect of EMI, loop size, crosstalk, decoupling, reflection, radiation, they can all be predicted and mitigated under the electromagnetic tools that we've learned in this class. So let's get into the consequences. To see why this really matters, let's consider a simple example. Imagine a medical wearable or implantable device where a high speed digital line was routed across a split in the ground plane. The return current can't follow directly beneath the trace, so it detours around the split, forming a large loop. Under normal operations, everything might seem fine until a high current motor nearby switches on and its rapid current change from an AC source produces a magnetic field spike. And because our loop is now effectively an antenna, Faraday's law tells us it'll pick up an induced voltage. Now, that voltage could corrupt a sensor reading or cause communication errors or send a communication protocol entirely out of timing. In life critical applications, that momentary glitch could interrupt the delivery of vital data or cause the device to end up in a recalibration state. So, even outside of medicine, we see similar consequences in automotive electronics, where an improperly routed ignition or injector line can radiate enough noise to reset the ECU and leave you stranded on the side of the road. Or maybe your Nintendo Switch controller just breaks down in the middle of a battle. So, while the failures may not always be catastrophic, the cost of poor electromagnetic design it includes system instability and unpredictable behavior, all of which are avoidable by applying these ECE 303 logic tests. In other words,